All right, so we're going to now work on a titration. The purpose of the titration is to find out what an unknown substance's amount of acid or bases, mainly protons or hydroxide. So if I have a container that has 3 hydroxides, well, obviously I would only need 3 protons to neutralize it, because the hydroxide plus the proton equals water. So again, 3 hydroxide, 3 protons neutralized. Good? Well, what happens if I don't know how many hydroxides are in here and I still try to neutralize it, and it takes me 6 protons to neutralize it? How many hydroxides had to have been in there? Answer: 6, right? So we just figured out how many hydroxides are in there. And that's the main point of a titration, right? It's to see how much of a proton or hydroxide you need to neutralize the other substance. So let's get to it. So in a titration, again, as I mentioned, it's used to determine the acid or base content of a solution. Now, with that solution, you got 2 parts. The titrant. The titrant is what you know, right? And then you're going to find out the concentration of the analyte. That's the unknown substance, right? If you have an unknown acid, you're going to titrate it with a base. If you have an unknown base, you're going to titrate it with an acid. So the concentration of the unknown is going to be determined based on how much of the titrant you're going to put in, right? And again, you're going to know the concentration. You're going to figure out how much you're going to add to it. Then you're going to figure out how much was needed to neutralize it. And it's going to be done through some calculations. So as I mentioned before, a proton plus a hydroxide is going to produce water, and that's going to have a pH of 7. It's neutral. And we need to use a chemical indicator to determine, hey, when it's neutralized, right? So we talked about earlier how we have different chemical indicators that will change color. The other thing that we could possibly use, if we had enough of them, are the pH meters. But as long as it's neutralized, we can say, all right, stop right there. That's enough. Now it's neutralized. The number of protons equals the number of hydroxide. Now, you've seen before in some of your previous labs that you can have a chemical change color based on whether it's acid or a base. In this case, the pink solution was phenolphthalein. With phenolphthalein, by adding base, it'll turn purple or pink. And if it's clear, it's acidic, or the pH is below 7. Now, to do the titration, we're going to use a piece of equipment called a burette. Again, in the burette, you're going to put something that you know the concentration of, the titrant. In your flask down here is going to be your analyte, the thing that you're going to analyze. The thing that you're trying to figure out is the analyte. That's in your flask. You're going to keep adding. You know the concentration. You're going to keep adding until it's neutral. That's going to give you a volume, right? Stop when you've neutralized it. And again, how do you know it's neutralized? You're going to use that indicator. When it changes color, right when it changes color with phenolphthalein, it's going to be close to pH 7. So that's when you know when to stop. In a future lab, what you're going to end up doing is you're going to be testing your analyte with your titrant, and you're going to keep adding until it gets to a nice light pink color. If you go beyond light pink and it turns into a magenta, that's a little bit too far. So an example of too far, that dark color is a little bit too far. It might be pretty, but that's not what you want. So now we're going to do calculations with the titration. Now, in this example, you have a solution of hydrochloric acid whose concentration is unknown. You titrate it using a 0.150 molar sodium hydroxide solution and find that 15.36 milliliters of sodium hydroxide solution are needed to neutralize 50.0 milliliters of the hydrochloric acid solution. Calculate its concentration. That's a mouthful. Again, it's overwhelming when you read it. So make sure that you can break it down and figure out what are you looking for. Here it says calculate the concentration. It's referring to the hydrochloric acid. So again, concentrations are going to be in molarity of the HCl, or another way to write down molarity of HCl is moles per liter of the HCl. Right? So that's your goal. Now, what's all this other stuff? Well, they told you the molarity, you know the molarity of that, and they gave you the volume of that. Again, the part of the titration that you know is called the titrant. You know the concentration, you know the volume. The part you are going to analyze is the molarity of the hydrochloric acid, but here they gave you the volume. The other part that's going to be important in these titrations is make sure you know what the formula equation is. All right? That's going to be important later on as we're going to use the mole ratio from the balance equation of the sodium hydroxide and hydrochloric acid. All right. So our board is a little bit short, so we're going to do a little shortcut. We're going to actually convert the volume of the acid into liters ahead of time, so it fits into our equation. So here, we start out with 50.0 milliliters of hydrochloric acid. We want to convert it into liters. So remember, when we convert, we put the unit that we want to cancel out on the bottom. We put a 1 before the prefix. And remember, if it's smaller than 1, it's going to have negative exponent. We learned that a long time ago. Milliliters of HCl cancel out. Get your calculator. You can get 0.050 liters of hydrochloric acid. Great. Save that for later. Now, let's get into the equation where we're going to start out with the 15.36 milliliters of sodium hydroxide. With this, we got to change it into liters, and just as we did before, put milliliters on the bottom so the units cancel out. Then we got liters here. We don't want liters in our answer. So how are we going to get rid of the liters? We're going to multiply it by the known concentration of 0.150 molars, and again, molarity, we can write down as moles over liter. Liters of sodium hydroxide cancel out. We got moles of sodium hydroxide. This is where our balance equation is going to come in. We have a 1-to-1 ratio. We don't want sodium hydroxide in our equation, so we're going to put sodium hydroxide on the bottom. Moles of sodium hydroxide cancel out. We got moles of hydrochloric acid. Wait. We're partly there. Remember, we're looking for moles of hydrochloric acid over liters of hydrochloric acid, right? So we got moles, good. We're gonna keep it. Then our liters, oh yeah, remember that little thing that we did earlier? We're gonna put that on the bottom, not the top, put it on the bottom, because again, we want moles over liters, liters being on the bottom. This does not cancel out, but it's okay. It's what we're looking for, moles over liters. And then at this point, we just put it into our calculator and get the final answer. All right, moving on to the next problem. Our next problem, slightly different. You titrate 25.0 milliliters of an unknown magnesium hydroxide solution with 34.21 milliliters of 0.250 molar nitric acid. Calculate the concentration of the magnesium hydroxide solution. And again, a lot of information. Break it down. I got to calculate the concentration magnesium hydroxide. That means concentration, molarity, of magnesium hydroxide. Another way to write this, moles of magnesium hydroxide over liters of magnesium hydroxide. That's our goal. That's what we're trying to get to. Our known information, our titrant is 0.250 molars, and we're going to be using 34.21. Right? We also have a known volume that we used of our analyte. Our unknown is 25.0 milliliters. Now, again, our board is too short. Do a shortcut. Let's work on the volume of the magnesium hydroxide and convert it into liters. Before I do that, we need a balance equation. Oops. Take a look at the balance equation compared to the last equation that we had. What is different? The difference is we no longer have a 1-to-1 ratio. We have a 1-to-2 ratio. So that'll be coming into play later on in the equation. Now, we have to do a little bit of converting. We're going to convert the milliliters of magnesium hydroxide into liters. And again, as we talked about before, we're going to put milliliters on the bottom so it can cancel out. We put a 1 in front of the prefix, 10 to the -3, because negative is for smaller numbers. Get your calculator, plug and play, you get 0.0250 liters. All right, so now that we have the volume magnesium hydroxide, now we can start with the nitric acid, our titrant that we know the concentration of. So we have milliliters here. Again, we have to change it into liters, so the molarity has liters on the bottom, so we can cancel that part out. So now that we have milliliters of nitric acid on top and on bottom, we can cancel it out. Now we have liters of nitric acid. We don't want liters of nitric acid. So what are we going to do? Cancel it out with our molarity. We're going to put the liters of nitric acid on bottom, liters of nitric acid on top, cancel, cancel. Then we have the moles. That's where we're going to get to here. Our mole ratio is no longer a 1-to-1 ratio, so make sure you have your balance equation and know what the ratio is. So in this case, we got moles of nitric acid on top. We're going to put moles of nitric acid on the bottom so it can cancel out. We're going to put the moles of magnesium hydroxide on top because that's what we're looking for. Remember, our goal's over there. Moles of nitric acid cancel out. We got moles of magnesium hydroxide. Wait, we're halfway there. Told you we're looking for moles of magnesium hydroxide over liters of magnesium hydroxide. So we're going to keep this. Now we need liters. Oh, look. Remember how we calculated this earlier? Now we're going to put it on the bottom. Now again, the liters is on the bottom. Do not multiply it. You're going to divide it. You're going to put the liters of magnesium hydroxide on the bottom. Again, we want to keep the liters because we want moles of magnesium hydroxide over liters of magnesium hydroxide. At that point, everything is canceled out. We're good to go. Put it into your calculator, and hopefully you get an answer of 0.171 molar magnesium hydroxide. And the next problem. All right. Volume of 0.200 molar sodium hydroxide needed to titrate 100 milliliters of 0.300 molar nitric acid. Again, we need a balance equation, but let's stop and figure out what we need. We need to determine the volume of sodium hydroxide. So the volume could be liters. We're going to calculate milliliters of sodium hydroxide. We have our titrant, again, what we know the volume, the concentration of, and we know the volume of the nitric acid. So change our volume of nitric acid into liters. Again, it's because we don't have enough space. Milliliters of nitric acid cancel out. Liters of nitric acid is there. Great. Now we can use that to calculate with our molarity. 0.100 liters times the molarity. Our liters of nitric acid cancel out. We got moles of nitric acid. Relationship between nitric acid and sodium hydroxide here is going to be a 1:1 ratio. Moles of nitric acid on the bottom, so we can cancel out. One on top, one on the bottom, good to go. We got moles of sodium hydroxide. We don't want moles. We want milliliters. Be careful of that. MOL versus ML. We have our molarity of sodium hydroxide there. So this time again, remember, this is moles per liter. We already have a moles of sodium hydroxide on top, so we're going to have to put the moles of sodium hydroxide on the bottom in order for it to cancel out. One more time. The moles of sodium hydroxide is already on top. We want to put moles of sodium hydroxide on the bottom so it cancels out, which means we're going to have to do the reciprocal of the number. We're going to have to flip it, right? Normally, it's 0.200 moles per liter. I want to put the moles on the bottom, so it's going to be 1 liter to 0.200 moles, right? So here we go. We're going to flip it. Moles of sodium hydroxide cancel out. We got liters. I prefer to have the volume in milliliters. Put liters on the bottom so it can cancel out. Milliliters up on top. Liters cancel. Milliliters left over. That's what we're looking for. Every other unit's canceled out. All we have to do now, throw it into your calculator, plug and play, and hopefully you get the answer of 150 milliliters of sodium hydroxide.